Hello and welcome to the Chapter 9 Summary Worksheet from Stevens' Introduction to Statistics, the Think and Do book. In this worksheet we're going to take a problem from each section, 9.1 to 9.3, and do it from beginning to end. And it's worth knowing that these solutions, as you see here, are given in the student version in the back of the book. So they should be in your book, whether you are a student or a teacher. Okay, so the first problem is going to deal with means. There's two parts. There's actually one part that deals with Chapter 9.1, and the other approach is Chapter 9.2. So you have a company that employs 30 people, and you want to study the effectiveness of a motivational speaker on employee satisfaction. These motivational speakers are expensive. You want to see if it's worth the money. So you create a survey that has the question. One of the questions is rank your satisfaction on a scale of 1 very unsatisfied to 10 very satisfied. And so you want to use the results of this survey to determine whether or not the motivational seminar improves satisfaction. So in the first case, in the first scenario, we're going to do a test. We're going to do a paired data test, right? A test for a mean difference, right? And by the way, all of the tests about means are t-tests, right? Because you have to use the t-distribution. When we talk about proportions, we use the z-table. So this is a t-test on paired data. So the first way we set this up is we take 10 employees to attend the seminar, randomly select 10 of them, and you give the survey to these 10 these 10 employees before the seminar, and then again 2 weeks after. And the table gives the results. Oh, dropped my pen. So right here we have 10 employees, but they're in pairs. There's a before and after. So this is one employee. Before the seminar had a satisfaction level of 2, and after the seminar had a satisfaction level of 2, so nothing changed. So that's one employee. Here's another one, again no change. Here's another one, there was an increase. And this one a decrease. So the point being here is that the data we're working with comes in pairs, right? And the test we want to claim is that satisfaction levels are significantly greater after attending the seminar. And we'll use a 0.05 significance level. Okay, so what we do here is we're going to let mu sub d represent the population of differences, the mean of the population differences, and the differences here come from, the sample differences come from here. So basically what we do is we take the larger value, the y's, which is usually the larger but not always. It has the y values after the seminar. It does have a higher mean. So we create this row of differences, right? And that's actually the data that we will test. Right, so our 2 sample problem has really turned into a 1 sample of differences. So after we get these differences, and I do this from y minus x, meaning I take the bottom number minus the top. In these first 2 cases, it doesn't matter. But notice this 2 comes from 7 minus 5. The negative 1 comes from 4 minus 5. 2 comes from 8 minus 6, and so on. So I create a row of differences, and I have a mean difference, a variance of the differences, and a standard deviation of the differences. Okay, so my claim is that the mean difference for all employees is greater than 0, meaning satisfaction levels have gone up. And the null hypothesis gets the equal to sign, and the alternate hypothesis supports the claim. So we look at the test statistic from Chapter 9.1, right? 9.1, and we have d bar. That's the sample mean difference. That's the 1.1. We have mu sub d, which comes from the null hypothesis, the assumed difference. The standard deviation of the difference of sample means, or no, the standard deviation of the sample differences. So that's this, 1.4. And then the number of data pairs. There are 10 pairs here. And so when you plug all this into your calculator, remembering to close this in parentheses, you get a test statistic of 2.48. And now we have to determine whether or not we reject the null hypothesis. We're using the critical values. Remember, this is a t-test, so I need 0.05 in one tail, 9 degrees of freedom. That came from n minus 1, because n equals 10. Right, there's 10 data pairs. It's one tail, so we get our critical value from the t-table. 0.05, one tail, 9 degrees of freedom. I'm going to try to remember that. Okay. So it's one tail, 0.05, so I'm in this column, 9 degrees of freedom, so I'm in this row. And the critical value is 1.833. So we'll take that back to our problem. 1.833, that's where this came from. Right, and so I didn't draw the distribution, but if I did, I would put my t distribution here, t values, and 1.833 would be somewhere over here. And the rejection region would be everything to the right of 1.833, because this is a right tail test. So if you look at 2.48, the test statistic, it is certainly in the rejection region. Right? Because it's in the rejection region, we reject the null hypothesis. All right, if you have software, you can get a p-value on this test statistic, and it's 0.0175. And since alpha, the significance level, is 0.05, our p-value is smaller than the significance level, and again, we reject the null hypothesis. So either way, table users or software users, we end up rejecting the null hypothesis. So that means we get to support our claim. So at the 0.05 significance level, the data supports the claim that satisfaction levels are significantly greater after attending the seminar. Right? So that's good. And what I mean by significantly greater is that it is unlikely that this increase in self-reported satisfaction levels is merely due to random variation. And the p-value tells us how unlikely that is. If you look at the p-value, and that came from software, p equals 0.0199. If you convert that to a percent, that's about 2%. So what that means is you could expect a difference of 2% before and after due to random variation. You can expect a magnitude of the difference observed here in this sample to occur 2% of the time just by random variation. Right? So that difference is fairly unusual because a difference that big or bigger would only happen 2% of the time. So that makes it unusual. It tells us that this difference is significant. You know, it might be due to random variation, but that is unlikely. Okay, so moving along to the second version of this investigation, where we're going to do a t-test again, and the t-test just means I'm using the t-distribution. I'm going to set this up as a problem with independent data. So what I do is I select 10 employees to attend the seminar. 2 weeks later, I give all 30 employees the satisfaction survey. Right? The 10 who attended and the 20 who did not. Right? So there's no before or after. There's some that attended, some that did not. And the results are given in the table. The degrees of freedom has been calculated so that you don't have to go through that messy formula if you're doing these by hand. So we're going to test the claim that those who attended the seminar have a significantly higher level of self-reported satisfaction. Right? And so here's the data. From the 10 who attended the seminar, the mean is 7.3. From the 20 who did not attend the seminar, the mean is 6.3. So upon initial investigation, the mean level of satisfaction for those who attended is 1 unit higher than those who did not. And so we want to ask ourselves, is that a significant difference, right? I mean, in this case, we have the population data, so we're not really doing a hypothesis test. We're actually doing a significance test. Is that a significant difference? Is really what we're asking. Significant difference. In this case, it's a significant difference in one direction, in the sense of being significantly higher for those who attended. Degrees of freedom is given to you, so I did the that horrible formula, the worst formula of 9.2. And what we're saying is that mu1, those who attended, the mean for all those who attended, is greater than the mean for all those who did not attend. And again, we have population data here, but we'll treat it as sample data. And so instead of having mu1 greater than mu2, we need to set it up with respect to a single number where the difference is relative to a single number. So we're saying that mu1 minus mu2, if I subtract mu2 from both sides of this equation, is greater than 0. Right? Basically, I'm saying that these levels here, when you subtract these levels, or this mean, subtract that mean, it's going to be positive. It's going to be greater than 0. So we go to the null hypothesis. So that's our claim. The null hypothesis gets equality, and the alternate hypothesis supports the claim. And we need to get the test statistic and degrees of freedom. The degrees of freedom, which is all this nasty stuff, has already been calculated for you. It's 15. And the test statistic using equation 9.2 is here. And we have all these. The x1 mean is up here. It's 7.3. Right? x1 bar. And x2 bar is right over here. That's the 6.3. So it's 7.3 minus 6.3. Delta comes from the null hypothesis, and that's 0. Divided by A, and I calculate A here, the variance of the first sample. 10 divided by the first sample size, which is 10. So I get 1. B is the variance of the second sample, 6.5, over the size of the second sample, which is 20. So I get 6.5 over 20. So A is 1.000, B is 0.325. When I stick those into my equation for the test statistic, I get a test statistic of 0.869. So now we have to determine, do we reject or fail to reject the null hypothesis? And if we go with the critical value method, we need to put 0.05 into one tail with 15 degrees of freedom that was given to us. So we've got a one tail. Right, again, one tail. So we're in this row. So we look for 0.05. There it is. So that means we're in this column with 15 degrees of freedom. Looks like I have 1.753. Right? Critical value of 1.753. We'll take that back to our problem. T sub alpha, 1.753. And what you should notice is the test statistics, that's this, test statistic, 0.869, is not in the rejection region defined by a critical value of 1.753. Specifically, if I was to draw the t distribution, I'd have 1.753 here. Everything to the right is in the rejection region, but my test statistic is not in that rejection region. Right? Test statistic does not lie in the rejection region. Failed to reject H0. If you have software, you can calculate the p-value, which is 0.199, and that is certainly greater than alpha, because alpha, the significance level in this problem, is 0.05. So by either method, p-value method or critical value method, you're going to reject the null hypothesis. I'm sorry, you're going to fail to reject the null hypothesis. repeat, fail to reject the null hypothesis because the test statistic does not lie in the rejection region or because the p-value is greater than alpha. Right? Either reason, fail to reject. So what that means is we don't have enough data to support the claim. Specifically, there is not sufficient evidence to support the claim that those who attended the seminar have a significantly higher level of self-reported satisfaction. Right? So the point is, sure, if you look at these two groups, and that's the entire population of all 30 employees, the mean for those who attended the seminar is 7.3. The mean for those who didn't was 6.3. It is higher, but it is not significantly higher. It means that basically a difference of that magnitude could easily be due to a mere variation, right? A random variation, right? And the p-value actually gives you an idea of how unusual that value that difference is. And here, a p-value of 0.199, that's about 20%. So you'd expect, just due to random variation, you'd expect differences that large or larger 20% of the time or more. Right? So it is not a significant difference, and we cannot claim that the difference was large enough to be considered significant. Right? So in this case, so notice in the first case when we did paired differences, we actually did come away and say it looks like the seminar works. And notice the difference in means was the same. Right? So here, I want to get rid of you. So here the difference in means was the same, 1. Right? Actually 1.1. And that was a significant increase. But that's because this was paired data. There's not as much variation. When you take very similar data and have a difference 7.3 versus 6.3, the data is not paired, so there's more variation in this in the data. And so it takes a greater difference to be significant. So when we had the independent data, we actually did not have sufficient evidence to support the claim. All right, so those are means. We had the paired data and the independent data. So now we'll do a problem about proportions. That's from chapter 9.3. Suppose we have 2 coins. We have a quarter. We flip it 100 times. We get 57 heads. You flip a nickel 100 times and you get 46 heads. The results are summarized in this table. The standard error is given. So notice you have 57 heads out of 100 tosses for a sample proportion of 0.57. For the nickel, I have 46 heads out of 100 tosses for a sample proportion of 0.46. And I give you the standard of error here, or the standard error, so you don't have to worry about calculating that. And I want you to test the claim that the proportion of heads in all tosses of the quarter is different from that for the nickel. Right? So it's a claim of inequality. Test the claim at the 0.05 significance level. So if I let P1 be the proportion of heads in all tosses of the quarter, and P2 be the proportion of heads in all tosses of the nickel, we are claiming that P1 does not equal P2, right? We're claiming the proportion of heads in all tosses of the quarter is different from, that means not equal to, P2. But again, I have to have an actual number on the right-hand side, so I subtract P2 from both sides, and my claim is P1 minus P2 does not equal 0. My null hypothesis gets the equality. My alternate hypothesis supports the claim, and I have a two-tailed test on my hands here. So now we calculate the test statistic. Again, it would be brutally difficult, except I gave you the standard error in the table, so it's 0.07068. P hat, P sub 1 hat is proportion of heads with the quarter, given in the table. P2 hat is the proportion of heads with the nickel, 0.46. Divided by the standard error, I get a test statistic of 1.56. Right? And keep in mind, this is a Z score, so we're going to be using the Z table. So now we have to decide, do we reject or fail to reject the null hypothesis? Well, if we look at the critical value, it's 0.05 in 2 tails. Love using this Z table because it has this little thing at the bottom. Alright. Take 0.05 significance level, 2 tails. My critical values are plus and minus 1.96. Alright. That's where I get the 1.9, plus or minus 1.96. So if I was to use these critical values and sketch my rejection region, Z, I would have a negative and a plus 1.96 with the negative, 1.96 with the positive, and these would be my 2 rejection regions. Alright, and as you can see, the test statistic is somewhere over here. Test statistic. So the test statistic is not in the rejection region, so I failed to reject the null hypothesis. You can also get the p-value of my test statistic. Because this is a z-test, either option is available to us from the table in the back. So I'm going to erase this, and I will put up the graph that corresponds to a p-value. Having trouble with my eraser here. Doesn't seem to be erasing very well, but we'll get there. Okay, so if I want to get the p-value, my distribution, the same as it always looks, bell-shaped. Z, so my p-value of the test statistic means I take my test statistic, 1.56, and anything more extreme than that is to the right. So the p-value would be this area here, right? But since this is a two-tailed test, I actually have to consider anything to the left of negative 1.56. Right? So if I'm to the left of negative 1.56 or to the right of positive 1.56, that's more extreme than 1.56. So then my p-value is the combined area. That equals the p-value. So let's just find this area and then we can double it. So if you look up negative 1.56 in the Z table, negative 1.56, there's negative 1.5, 6 is down here, I'm at 0.0594. We'll take that back to our problem. So this is I'm differing from my, I guess whenever I did this answer in the back of the book, it looks like I'm taking the p-value, I'm taking 1.56, taking the area to the left and subtracting that from 1. But if I take 1 minus 0.9406, I will get 0.0594. Right. So 0.0594 is that area. And if I double it, if I take 2 times 0.0594, I will get 0.1188. Right. So either way, you can do it. But you basically have to find the area of both tails to get the p-value. So you get 0.1188, and regardless of which way you do it, that is bigger than alpha because alpha in our case is 0.05. So whether you use the critical value method or the p-value method, you're going to fail to reject the null hypothesis because the test statistic is not in the rejection region or the p-value is bigger than alpha. Alright, so if I fail to reject the null hypothesis, I can't support the claim, and I say at the 0.05 significance level there is not enough data to support the claim that the proportion of heads in all tosses of the quarter is different from that for the nickel. Right? So notice that actually worked out because look, our claim was that they did not equal. All right? And our null hypothesis was that they do equal. And so we could not reject this. So we could not accept that they were not equal. We didn't prove that they were equal. We just could not accept that they were not equal. Crazy, right? The double negatives don't always make a positive. Okay. Do these results demonstrate that the coins are fair? Right? Basically, all we said was that there's not enough reason to believe that the proportion of heads is different between them. Does that demonstrate that that both coins are fair? Certainly not. Right? All we said was that whatever the proportion of heads is, there's not enough reason to believe that the proportion for the nickel is different from the proportion for the quarters. All right? We didn't demonstrate that they both equaled 0.5. Really, to prove that both coins were fair, you'd have to deal with the quarter and then the nickel and test the claim that P equals 0.5 for the quarter and P equals 0.5 for the nickel. So you'd have to do 2 single sample hypothesis tests. All we did in this example was demonstrate that the difference in sample proportions was not great enough to safely conclude there was a difference between the 2 coins. We did not conclude that both coins were fair. All right, so that's one example from Chapter 9.1, one example from Chapter 9.2, and one example from Chapter 9.3, thus wrapping up Chapter 9 and concluding the Chapter 9 summary worksheet. So if you're still with me, I guess I'll see you in Chapter 10. It's been a pleasure having you. Have a good day. Bye.